Alright, let me give you a quick little heads up. I'm going to go through these answers. The ones that involve writing, I will actually write out and explain, but a lot of the answers have already been completed for you, and you'll see the typed answer. Some of those I'm not going to spend more than maybe 3 or 4 seconds on them, where others I'll explain a little bit more thoroughly. But I'm assuming that you're going to hit the pause button and you're going to not be upset that I'm going too fast. Instead, you're going to hit the pause button so you could actually read all of those answers. So if I'm not explaining something, if I'm just scrolling through various answers, you're actually going to hit the pause button in between and actually read what's written on the screen for you. All right, to start with, it says the mole. You should be able to convert between particles, mass, volume, and the mole, and so forth. This is important to remember. Anytime you see the word atoms, molecules, ions, any type of things, you're going to use the 6.02 times 10 to the 23rd before that. If you see grams, the only number you put with grams are the masses found on the periodic table. So you'd never put 6.02 times 10 to the 23rd next to the letter G in a dimensional analysis problem. So if you see G, you put masses on the periodic table. And if you see liters, if you're using liters and you write down liters, 22.4 is a magic number that always goes with liters. And the only number you put with the unit mole is 1. For our purposes, anytime you see the number or see the word mole, a 1 should be right next to it. Never put 6.02 times 10 to the 23rd moles. That's wrong. It's 6.02 times 10 to the 23rd atoms in 1 mole. So they'll be opposite each other. All right, remember this. 1 mole of any gas takes up 22.4 liters of space as long as, see big capital letters here, as long as conditions are STP. Standard temperature and pressure. So you should know the different values for standard pressure. We got 1 atm, we got 101.3 kilopascals, and we have 760 millimeters of mercury. And standard temperature is 0 degrees Celsius, which is equivalent to 273 Kelvin. So you should be familiar with all that. All right, let's work out our first problem here. We're converting the moles of carbon dioxide to mass. Well, we're dealing with mass, so we have to look on the periodic table. So we're going to add up 1 carbon, which is 12.0, and we're going to add up 2 oxygens, which is 16.0 times 2, so that's 32.0. And then we add up the 12 and the 32, add them together, and you get 44.0 grams. So that's the molar mass of carbon dioxide. That's if I had 1 mole, but the problem says I have 3.4 moles. So I'm going to do dimensional analysis. 3.4 moles, and then remember whatever you wrote there, you absolutely immediately put down here. There shouldn't even be a thought in your mind as to what to do next. If you see the word moles there, you put moles there. If you see the word chickens there, you put chickens down here. Then you put what you're solving for. We're solving for grams, that goes on top. Remember the number 1 always goes next to the word mole. We talked about that up here. And 44 is the mass of 1 mole off the periodic table. Multiply across the top, divide through by the bottom, which you don't really need to do. And you should get 149.6 grams. So that's how many grams 34 moles is equal to. All right, next problem. It says molecules. So anytime you see the word molecules, atoms, ions, and so forth, you're going to use that 6.02 times 10 to the 23rd. So how many molecules are contained in the sample? Well, the only thing you know is that the sample is 3.4 moles. So start with that. Remember, whatever you write over here, you immediately put on the bottom. So you're going to put moles down here. And then you're going to look for molecules. So you write molecules up here. Remember I said don't abbreviate the word molecules because you could get it mixed up with moles. Atoms, ions, whatever. If you want to abbreviate, go ahead. But try not to abbreviate molecules. All right, 1 always goes with moles. 6.02 goes on top here, times 10 to the 23rd. Don't forget about your exponent. And then you do the math, and your calculator should show something to the effect of 2.05. And again, don't forget your exponent, and don't write EE. Write the times 10 to the 24th, and then your unit is molecules because moles cancels out. Okay. What would the volume of the sample be? Well, now we're dealing with volume, and it's a gas, it's carbon dioxide, so you can run this problem. We would never try to trick you, but if it did say what would the volume of the sample of, and it was a liquid substance or a solid substance, you would do maybe water displacement, or you would put it in a graduated cylinder and figure out the answer there. You could not use 22.4 liters. It's only used for gases. So we start with what we know, 3.4 moles times, and then you put 1 mole on the bottom, and on top 1 mole is equal to 22.4 liters, just about 11 soda bottles if it's at STP. So multiply across the top, 3.4 times 22.4, that is 71.7, and that's liters. Moles cancels out, so we're left with liters, which is good because that's what the problem asks us for. Okay. All right, number 4, it says, what must the temperature and pressure for your answer be in the previous question to be correct? It has to be at standard temperature, 0 degrees Celsius, which later on when we do gases has to be converted to Kelvin, and standard pressure, which is 1 atm, 101.3 kilopascals, 760 millimeters of mercury. We even talked about 14.7 pounds per square inch, so this is PSI if you're dealing with the English system. Number 5, which would have a greater mass? A sample containing that many atoms of mercury, or a sample containing the same molecules of fluorine here? So we're going to say, well, they both have equal number of particles, but we have to compare the masses on the periodic table. So if we compare the mass of mercury versus the mass of F2, mercury would have a larger molar mass, so it would have a greater overall mass. Okay. If there were different numbers of particles here, if this said 5.8 times 10 to the 23rd and this said 7.95 times 10 to the 23rd, we would have to convert it to a mole and see what the final answer would be that way. Okay, more calculations. It says calculate the percent of hydrogen, sulfur, and oxygen in H2SO4. So the first thing we need to do is figure out what the grand total mass of H2SO4 is. And when you add up 2 hydrogens, 1 sulfur, and 4 oxygens, you should get about 98.1 grams. That's the total. That's kind of like saying, I want to know how many red, blue, and yellow M&Ms in a bag of M&Ms. Well, the first thing you need to do is figure out how many total M&Ms there are in the bag. And then we're going to do the percents. Percents are always part divided by the whole thing. So we're going to put the part of whatever color we're looking for. Let's say red. Red goes on top, divided by the whole thing on the bottom. So the whole thing is our 98.1 grams. And the first one I'll do is hydrogen here. Now I look at the equation, there's 2 H's, so I'm going to put 2.0. If there were 9 H's, I'd put 9.0 because each one of them is 1.0, and so forth. 2 divided by 98.1 is just about 2%, 2.0%. Okay, so there's my hydrogen. Let's do sulfur next. So sulfur, I look in the equation, there's only one of them. So the molar mass of sulfur off the periodic table is 32.1. That's just sulfur divided by 98.1, and then I come out to about 32.0% for sulfur. I'm sorry, 32.7%, my bad. 32.7%. And then finally the oxygen. Now there's 4 oxygens in there. Each one is 16.0. So 4 times 16 is going to be 64.0 divided by the whole thing. So this is going to be a much higher percent. And then you do out the math and you come out to about 65.2%. That's a 5. Okay, and there's your oxygen. So we figured out the percents of each by looking at the part that we're focusing on divided by the whole, and don't forget to look at your grand total number of atoms in the molecule and multiply that by its molar mass.